Hi, I'm Alex. In this video, we will introduce the key concepts for introducing and teaching algebra as a generalization of the arithmetic students in Year 7 and 8 have been familiarizing themselves with over their primary and early secondary years. Algebra is a way of using symbols and symbolic representations to think about and reason relationships in both mathematical and real-world contexts. Let's start by introducing the concept of pro-numerals, including variables. We can begin introducing the idea of generalizing arithmetic by giving several numerical expressions that have a repeated structure, starting with one number that changes from one expression to the next. We can show that we can describe this expression for any value by replacing the changing numeral with a symbol. The symbol can be a letter from any alphabet. Most common are the English and Greek alphabets, or a shape, or even an emoji. Students will have already worked informally with pro-numerals in primary school, with missing number problems and working with objects with a repeated but unknown value. We want to emphasize that where we see the same symbol in the same expression or equation, it refers to the same number each time. During this process, keep reminding students that each symbol or each letter stands in place of the number. The pro-numeral in the previous example was r and represents some number. It may be a known or unknown constant that has a fixed, constant value, or it may be a variable constant whose value can be varied. Consider your context. If students are nervous about the intimidating concept of algebra, use shapes, emojis, or other quickly reproducible images before introducing letters, as that can ease some anxiety by first building confidence and their fluency in their thinking. At this stage, you will be ready to introduce the word pro-numeral to students, which is literally pro, meaning in place of, numeral, meaning a figure or character standing for a number. A common misconception is that each letter has the value it is always equal to, such as a equals 1, b equals 2, c equals 3, etc. We can address this by reusing pro-numerals where it is used to represent a variety of values and directing attention to the fact that the same pro-numeral changes the value it represents in different scenarios. As a convention, we generally write pro-numerals in cursive style. This is particularly important when using x as a pro-numeral with the times sign. Now, we will talk about using the arithmetic laws for expressions. We want students to create links between the arithmetic laws and algebraic expressions. A key step here is taking familiar worded expressions for operations with numbers and writing algebraic expressions with them. Mathematical literacy is a key skill here, and students need to develop fluency with using the vocabulary for the four operations. Model examples with students, such as write an expression for the sum of x and y. Write an expression for the product of 3 and y. A common error is with subtraction, when students don't know which order to put the terms. For example, the expression representing 6 minus h will be different from 6 subtracted from h. However, students often write 6 minus h for both, as the 6 appears first. It is worth being as pedantic with addition and the difference between 6 plus h and 6 is added to h to emphasize to students the terminology of subtracted from and added to, as the number that follows those phrases will appear first in the expression. Keep in mind, this is the reverse of multiplication and division, which say by instead of to or from. At this stage, it is important to model the correct notation and algebraic conventions to students. Some of the key algebraic conventions students need to be familiar with include 10 plus a is the same as a plus 10 due to the commutative law of addition. 10 minus a is not the same as a minus 10. The order matters for subtraction, but 10 minus a is the same as 10 plus negative a, and so the same as negative a plus 10. 7a means 7 multiplied by a. It is worth telling students that since we use x as a pro-numeral so often, we want to avoid writing the times sign, as the two can be easily confused. 7 plus b times a plus 3 means the sum of 7 and b multiplied by the sum of a and 3. ab means a multiplied by b and is the same as ba due to the commutative law of multiplication. 7a is the same as a7 due to the commutative law of multiplication, but there is too big a risk that it may be confused with the poorly written a to the power of 7, so we tend to avoid writing it in that order. A over 3 means a divided by 3, as well as 1/3 times a. N squared, and how that is different to 2 to the power of n. We can now revisit writing and working with algebraic expressions, but now involving multiple operations. For this, function machines are useful. When using the function machines, students need to work from left to right, starting with the input. Examples should include questions that apply to various operations, applied to numbers, not necessarily evaluating each expression, and then applied to pro-numerals to show how the algebraic expression captures all possible inputs in one expression, using grouping symbols where necessary. Use examples where the order of operations is changed so that students can compare and contrast the different expressions. Connect this back to writing expressions from word descriptions so that students can identify how subtle changes in the language impact the order of operations. Consider the following pair. Example 1. The product of 5 and 6 plus x. Example 2. The product of 5 and 6 plus x. Verbally, we can make that distinction by pausing longer where the comma is, to emphasize what the product is of, the 5 and the 6, or the 5 and the sum of 6 and x. Other phrases to look out for are ordering phrases such as then, which tells the reader the succession of operations, much like a function machine. With students becoming more familiar with the order of operations applied to pro-numerals, we can look at substituting the pro-numerals with specific numbers to evaluate the expression, which means to find the value of the expression. When substituting into an expression, a common misconception is students writing the numeral they are substituting without considering algebraic conventions, such as AB meaning A multiplied by B. So, for example, if A is equal to 4 and B is equal to 6, to find the value of AB, students may write the answer as 46 instead of 4 times 6 is equal to 24. Or, if A equals 4 and B equals -6, students may write 4 minus 6 is equal to -2 and not 4 times -6. To help address these issues, we place the substituted numerals in brackets where the pro-numerals were and use the algebraic convention that we apply multiplication between the brackets. We also want to begin with different numbers throughout the expression we are substituting into, including the numbers you are substituting. For example, when substituting with n squared, don't start with n equals 2, as it is no longer clear which 2 is performing which function, as well as it looks like we are doubling and not squaring. Whereas if n equals 3, it is clear that we are multiplying 2 3s. But for n cubed, consider not using n equals 3 for the same reason. This is not to say never use 2 squared or 3 cubed, only not to use them as your introductory examples. To add and subtract algebraic terms, they need to have exactly the same algebraic factors, because it is an application of the distributive law. For example, 3 times 4 plus 5 times 4 is equal to 8 times 4. We also have 3 times a plus 5 times a is equal to 8 times a, which is the same as 3a plus 5a equals 8a. That is, we are using the common factor of a to group the terms together. What we don't want to say is I have 3 apples and 5 more apples, together I have 8 apples, so 3a plus 5a is equal to 8a, as this reinforces the idea that the pronumeral is an object and not a number. A could represent any number of apples, or even the cost of an apple, but it is not itself an apple. If we don't have exactly the same algebraic factors, we still have algebraic factors in one or more terms that won't group together. This is why in an expression like 3x plus 5x squared doesn't group together nicely, because the highest common algebraic factor is x, which is not the entire algebraic factor of both terms. Algebra tiles are useful for visually showing the difference between x and x squared terms. Algebraic terms that have the exact same algebraic factors are often called like terms. If we expand the product of powers of algebraic factors and write them in the same order, we should have exactly the same product. Students often have a misconception that it only needs to have the same letter. Once students have mastered simplifying algebraic expressions, they can build on this with expanding brackets. Students will be familiar with the area model for chunking and multiplying larger numbers from primary school. This prior knowledge can be developed further by applying it to expanding single brackets. Try to avoid using an example with a constant or coefficient of 1 as the first example, such as 2 times x plus 1, when you first introduce this concept, as students may not see the distributive link of expanding the brackets as they don't physically multiply. They instead copy the 2. Action arrows are a key step in working out here that will help students to remember to multiply the whole bracket. A common misconception is only multiplying out one term in the bracket. Algebra tiles are also a useful tool for expanding brackets. The yellow squares represent the constants, the green tiles the pronumeral x. The array model multiplies 2x by 2, resulting in 4x, and 3 multiplied by 2 is 6. Reference can then be made to like terms by explaining that this cannot be simplified further. Expanding brackets can be linked back to the simplifying skills by expanding 2 brackets and then simplifying. The scaffolding and steps of the method ensure students develop a systematic approach, ensuring they multiply negative numbers accurately and simplify terms. For students who have an earlier understanding of negative numbers, they can have scaffolds such as number lines to help them simplify algebraic expressions. Factorizing expressions is the reverse process of expanding brackets. It involves writing an expression as a product of its factors. At least one of those factors will have 2 or more terms. A useful teaching strategy here is to activate the prior knowledge of highest common factors before starting factorizing, with a starter or an activity. Emphasize the language of factors and the highest common factor. The area model is again a useful tool here, which students can apply in reverse using factors. Start with expressions like 2x minus 6, which have a common factor of 2. Show students how to factor it out. 2x minus 6 is equal to 2 times x minus 3. The takeaway message of algebra should be that we are generalizing arithmetic and looking at number concepts in more and more different ways as we advance further into algebraic ideas. Always consider what numerical idea is being generalized with algebraic notation and use that as an in to introducing the next idea along.